Hi everyone, this is Becky, and in this video we are going to take a closer look at gas pressure. Okay, so remember, thinking back to physics, that pressure is defined as force exerted per unit area, or force over area. Remember that the units of force are a Newton, the units of area are a meter squared, so a Newton per meter squared is the same thing as a Pascal, which is the SI unit for pressure. So the typical classical way to think about pressure is to think about someone stepping on your foot, all right? And if an elephant steps on your foot, it hurts, but if an elephant wearing stilettos steps on your foot, oh my God, right? Because the elephant in stilettos is obviously exerting a higher pressure because the surface area of the shoe is smaller. Same thing here with the elephant and a figure skater, right? The figure skater is actually exerting a higher pressure on the ice. And the elephant is on the ground simply because of the tiny, tiny surface area of the skates, okay? All right, so how does all of this apply to gases? How can we think about this with respect to gases? So say that I have a container. Sorry, picking the color. Here's my container. My container contains air or some other sort of gas molecules. And so here's my molecules that are in here. They're spread out really far apart. And the thing is that these molecules are moving, and they are moving pretty quick. So we have velocity, vector arrows moving here. And as these molecules are moving, they're colliding with the side of the container. And so you got thinking about the force of the collision, the force of those molecules colliding with the side of the container over the surface area of the container. I apologize, my dogs are barking in the background over what I'm not quite sure. So thinking about this, we're looking at the force of the collisions, the force of the collisions of the gas molecules against the side of the container is what's exerting that pressure, what's causing that pressure. Pressure, or atmospheric pressure, this is the gas pressure that most of us are used to. So the atmospheric pressure is caused by the weight of the atmosphere, essentially just like pushing down on us down here on the bottom. Right, because gravity pulls the air down, and so the weight of the air molecules is exerting a pressure on us. And so remember that, again, we're talking force per unit area. So if I have a square inch column of air above me, that square inch column of air is exerting about 14.7 pounds of pressure. So 14.7 pounds per square inch of pressure. Remember that pressure units, although we said the SI unit is a Pascal, we can also think about this as any unit of force per unit area. So pound or pound per square inch is a unit that we can use for pressure. And then there's some other units that we use specifically to talk about gas pressure, which we'll get into in a second. So PSI, pounds per square inch, is a unit of pressure. And we don't notice atmospheric pressure just because we're used to it. Like thinking about it, like, okay, so if I'm looking at my thumbnail, the atmosphere is essentially pushing down the weight of a bowling ball on my thumb, but I don't feel it because I'm used to it. Now, if I put a bowling ball on my thumb, then I'm all of a sudden feeling twice the pressure, and I'm going to feel that, and that's going to hurt a lot. But I don't typically notice normal atmospheric pressure. When I'm going to notice it is like when my ears pop on a plane, or like if I'm diving, I'm going to notice a change in pressure. That's what I'm going to notice because it's not what I'm used to, right, when it changes. Remember that the atmospheric pressure is going to depend on altitude, it's going to depend on temperature, it's going to actually also depend a little bit on humidity and some other stuff. But, all right, so we know that the atmosphere is pulling down on us and it's exerting a force, a pressure on us. How do we measure that pressure? Well, so much more. Measure that pressure by using something called a barometer. And so a barometer is basically thinking about, okay, the atmosphere is pushing down. How large of a column or how high of a column of a particular liquid can the atmosphere support? And the higher the column, the higher the pressure is. Think about this like the inside of an aerosol can or like a butane lighter or something like that, right? So the atmosphere is pushing down here, which is causing the liquid here to raise up into the tube. I can do this with water. If I do this with water, atmospheric pressure will support a column of water that's essentially 34 feet tall, which is pretty tall, which is why we use mercury. Typically use mercury where it's 760 millimeters, so it's about 2.5 feet, which is a much more reasonable number or amount to deal with. And remember that this is a vacuum. This is true because mercury is so much more dense than water is. So it's so much more dense, which means it's heavier per, like it exerts more force, so it takes higher column to measure it. All right, so when I measure the atmospheric pressure, typically what we think about as standard atmospheric pressure is, will support a column of mercury that is 760 millimeters tall. So we say it's 760 millimeters of mercury. 760 millimeters of mercury is the same thing as 101.325 kilopascals. Pascals, remember, is a really teeny tiny unit. So we use kilopascals just to make it easier to deal with. It's the same thing as 760 torr, is the same thing as approximately 1 atmosphere. Okay, so all of these units are interchangeable and we use them to measure atmospheric pressure. Okay, so we use a barometer to measure atmospheric pressure. To measure pressure inside a container, we can't use a barometer, but we can use something called a manometer. So a manometer, words, right, is used to measure the pressure of a gas inside a container. So a couple different types of manometers. You can have an open end or a closed end. This is a closed end, you have a vacuum in here. So you don't have any, there's nothing pushing down here. So you just have the gas that's in the container pushing down on this tube here. Remember, this is a continuous flow of mercury. So the difference in height here, so the height of this column is the pressure in millimeters of mercury. Right, when the barometer is open end, we have the atmosphere pushing down, the gas pushing down here. So pressure, the atmosphere, so that the height here is the pressure of the gas minus atmospheric pressure is equal to atmospheric pressure minus the height, right? So if this column is lower, that means there's less pressure. If it's higher over here, there's less pressure. And if it's higher over here, there's more pressure, right? So same thing here. This is the same kind of open end here. In this case, the gas pressure inside the container is bigger because it's pushing down more, right? So the height of the tube here is equal to the pressure. So the difference in height here is the pressure of the gas inside the manometer. Right, important thing to note here is remember that you're measuring the height in millimeters of mercury, so that's going to be your unit of pressure. Atmospheric pressure over here is 760 millimeters of mercury. These are kind of like, right now we have a pressure sensor, which essentially does the same thing that this does, but it's useful to think about what's happening here and causing the difference in height and how we can use that to our advantage. Okay, so reminder, just recap or thinking about, if I have gas that's inside a container, these gas molecules are moving, they're really far apart, and they're moving at pretty high rates of speed. As they're moving at high rates of speed, they're colliding with the sides of the container. As they collide with the side of the container, they exert a force that comes from the collision. And we're talking about the area of the container. So this is what we're looking at in terms of pressure. That's what's exerting the pressure, is the collision of those air molecules with the sides of the container. We can change the pressure inside the container by changing the area, so changing the volume, the surface area, so changing the volume, by changing the force of the collision, by changing the number of collisions. All of these things will affect the pressure, as you saw with the syringe activity that we played with. Okay, so what I want you to think about are things that I want you to be comfortable doing. And remember that you can use the textbook here. There's some example problems that are given on the unit by unit page on Canvas that concern this. Is you should be comfortable converting between pressure units using dimensional analysis. So the idea that 760 millimeters of mercury is equal to 760 torr is equal to 1 atmosphere is equal to 101.325 kilopascals. So you should be comfortable working with those units, and that's just the same as we've always done in terms of dimensional analysis. And then you should be comfortable reading pressures from an open or closed end manometer. Remember that you're just talking about here is a difference in height between the two columns. And if it's the one that's connected to the container that's higher, then the pressure inside the container is lower. So these are the types of things that you should be okay doing. Try a couple of the practice problems in the textbook if you don't feel like you could be comfortable with this. We will do some more work in class on the next time we meet when we start doing math. So just be aware of that. There will be a chance to practice and ask questions. bring any questions that you have about gas and gas pressure to class next time we meet, and I'll see you then.